Hi everyone, my name is Dilip Patel. I'm a former data scientist turned AI product leader with 12 plus years of experience building and scaling AI systems across pricing, risk management, personalization, retrieval, ranking, and recommendations. Objective for today's talk is to show a fraud detection system is not only highly accurate but also explainable so risk team can act on it with confidence. I'll walk through the story in 6 short steps. Here is the agenda: problem, prior work, method, results, explainability, and takeaways. Let's start with what we built and why it matters. Payment fraud detection is hard for 3 reasons: high dimensional signals, severe class imbalance, and constantly evolving behavior. What we did is straightforward but disciplined. We cleaned and encoded the dataset. We reduced noise with feature selection. We fixed imbalance with SMOT. And then we used a stacking classifier combining XGBoost, LightGBM, and CataBoost. Headline result is 99.75% accuracy. And we explain decisions with SHAP and LIME so analysts can trust the system. Now I'll frame the real operational problem: why accuracy alone isn't enough. Digital payments are growing fast. That increases transaction volume and it increases the fraud surface. Rule based systems struggle. They are brittle. They lag new attack pattern. Machine learning helps, but many models are black boxes. That creates a new risk. If we can't explain what a transaction is blocked or why a transaction is blocked, we lose trust and create operational drag. And regulators increasingly expect transparency. So the goal is two parts: detect fraud well and explain it clearly. Next, a quick look at what others have done and what gap we targeted. I won't read every paper. Here is the pattern. Many approaches focus on accuracy, leveraging deep learning, boosted tree ensembles. Some do add explainability, but often at the cost of performance or limited operational usability. Our gap is practical. We want a model that is stronger under imbalance, robust under drift, and explainable at both global and per transaction levels. Now I will show the exact pipeline we used from raw labels to an explainable decisions. This slide is the whole system. Step 1, we start with the IEEE CIS fraud datasets. Step 2, pre-processes. We remove unique IDs, handle missing values, and encode categories. Step 3, feature selection. We reduce noise and dimensionality. Step 4, we fix the imbalance. We use SMOT to create synthetic fraud samples. Step 5, stacking classifier we build combining XGBoost, LightGBM, CataBoost. In step 6, we evaluate the precision, recall, and F1. And then we explain decisions with SHAP and LIME. Now the results. The first, the confusion matrix and core performance numbers we discuss. Let's interpret the confusion matrix. False positive create customer friction, and false negative create direct fraud or risk loss. So you need a balance. Table 2 shows stacking of these multiple algorithms in the form of ensemble wins over individual models. The accuracy reaches 99.75 with a strong precision, recall, and F1. Next, we'll discuss the threshold behavior, ROC, and precision recall. Because real fraud ops always tune threshold. The slide answers: does the model separate fraud from non fraud well across thresholds? As you can see, ROC curve shows that AUC is 0.99. That's a near perfect discrimination. The precision recall curve is critical under imbalance and it stays strong. That indicates you can tune sensitivity without collapsing precisions. What is the operational implication here? The matter this matters in productions. You can choose a stricter threshold during an attack, and then as fraud pressure reduces, you can relax it after, and still the performance stays stable. Now, let's discuss the explainability layer. What features drive decisions globally and locally? Explainability in a risk is a trust layer. First, the SHAP. The SHAP shows global feature importance. Top features like V17, V14, V12 have the great influence. This helps fraud teams validate whether the model is learning sensible signals. Second, Lime. Lime explains a single decision. You can see which feature push forward fraud and which push towards not fraud. This is exactly what analysts need for case review and escalation. And when we compare to the baselines, the stacking model outperforms BERT, CNN, AdaBoost. So we keep the accuracy and gain explainability. Let's close. What this means for real world fraud mitigation and what comes next. By leveraging a stacking of Ensemble, XGBoost, Light GBM, CataBoost alongside advanced pre-processing, we achieved a superior accuracy of 99.75%, outperforming baseline models. By integrating SHAP and Lime, we transformed a black box algorithm into a transparent, trustworthy risk decision engine. Future work is going to be about production reality. We will add streaming pipelines, concept of drift detection, privacy preserving learnings, and hybrid architectures that bleed deep learning with boosted ensembles. Here are references that supported this research. Thank you for listening. My contact info is on the slide. Please reach out for any question. I really want to thank you, ISDFS 2026 Program Committee, for having me. Thank you.